The dream of artificial gravity, why we need it in space. Ever since humanity dared to dream of long-distance space travel, artificial gravity has been a recurring element in our imagination, from rotating starships in science fiction films to massive space stations with internal gravity fields. The idea of recreating Earth-like conditions in the vacuum of space is more than just a technological fantasy. It is a fundamental necessity for the future of human exploration. But why exactly is artificial gravity so crucial? And what drives our pursuit of this technology? The answer lies in the profound and often debilitating effects of microgravity on the human body. While floating freely might seem fun at first, the absence of a constant gravitational force has serious and cumulative consequences for astronaut health. One of the most immediate impacts is bone loss. Without the constant load and stress that gravity applies to our skeletons, bones begin to lose density at an alarming rate, similar to severe osteoporosis. And this isn't just a matter of fragility. It also causes calcium to be released into the bloodstream, which can lead to kidney problems. On long-duration missions, such as a journey to Mars, re-entering Earth's gravity with severely weakened bones poses a significant risk of fractures. Muscles, too, suffer considerable atrophy. Like bones, muscles rely on constant use and resistance to maintain their mass and strength. In microgravity, even with strict exercise routines, the muscles, especially those in the legs and core, gradually weaken. This not only makes daily tasks in space more difficult, but also compromises an astronaut's ability to move and operate efficiently after returning to Earth. Muscle recovery can take months, and in some cases, the deficits may be permanent, but the problems don't stop there. The cardiovascular system is also deeply affected. On Earth, gravity pulls fluids downward. In space, this distribution changes dramatically, causing fluids to shift toward the upper body. This leads to facial puffiness and a constant feeling of nasal congestion. More concerning is the heart itself. It usually works against gravity to pump blood, but in space, it begins to relax, losing muscle mass and becoming less efficient. This can result in orthostatic hypertension, dizziness and fainting upon standing after returning to Earth's gravity. Vision may also be affected. There are reports of spaceflight-associated neuroocular syndrome, also known as SANS. It involves swelling of the optic disc and structural changes in the eye, possibly caused by increased intracranial pressure. The immune and vestibular systems are not spared either. There is evidence that microgravity can suppress the immune system, making astronauts more vulnerable to infections. Meanwhile, the vestibular system, responsible for our sense of balance and spatial orientation, becomes disoriented in the absence of a clear gravitational direction. This leads to nausea and confusion, also known as space sickness. While most astronauts adapt over time, the initial discomfort can be significant and may persist to a lesser degree. Beyond the physiological challenges, the lack of gravity creates operational and psychological difficulties as well. Simple tasks, like eating, drinking, or using the restroom, become complex. Tools float, liquids form drifting bubbles, and constant movement requires foot or hand restraints. The need to strap in to sleep or to perform any activity can be exhausting and reduce efficiency. Psychologically, the constant absence of a clear up or down can be disorienting and contribute to a sense of isolation in an environment that is already extreme by nature. Artificial gravity, therefore, is not a luxury. It is an imperative need for long-duration space missions, whether it's for building lunar and Martian bases, for asteroid exploration, or, in a more distant future, for interstellar travel. Artificial gravity would not only protect the health and well-being of astronauts, but also increase the efficiency and productivity of their operations, making life in space more similar to life on Earth, and as a result, more sustainable. It is the key to unlocking humanity's true potential as an interplanetary species, allowing us to live and thrive beyond Earth's cradle. Inertial challenges. How do we create artificial gravity? If the need for artificial gravity is so obvious, why don't we have it yet on our spacecraft? The answer lies in the enormous engineering challenges, the prohibitive costs, and the technological limitations that come with creating a simulated gravity environment. The main and most promising method for generating artificial gravity is through centrifugal force, using the principle of inertia. The idea is relatively simple, in theory. If a structure spins, objects on its outer edge experience a force pushing them outward, simulating gravity. The larger the radius of the structure and the faster it spins, the stronger the centrifugal force and the greater the artificial gravity perceived. Think of a giant carousel. The people on the outer edges are pushed outward. In space, a spacecraft in constant rotation would press its occupants against the outer walls, making them feel what, to them, would be the floor. However, putting this concept into practice is full of challenges. The first and most obvious is the size of the structure. To simulate 1g, that is, Earth's gravity, a significantly large rotation radius is needed to avoid unwanted side effects. A small radius combined with fast rotation can cause what's known as the Coriolis effect. The Coriolis effect is an inertial force that acts on objects moving within a rotating system, causing their paths to deviate. In a rotating spacecraft with artificial gravity, this would mean that when astronauts move, they would feel a strange lateral force, leading to disorientation, nausea, and difficulty walking. To reduce the Coriolis effect to a tolerable level, studies suggest an ideal rotation radius of at least 100 meters, and preferably 200 meters or more. Building a structure hundreds of meters wide in space is a Herculean task. Just think about the difficulties of launching and assembling components of that size. It would require a series of complex launches and in-orbit assembly operations, which would dramatically increase both cost and logistical complexity. The International Space Station, the ISS, which is relatively small compared to what would be needed to generate artificial gravity, took years to build and cost billions of dollars. A spacecraft with artificial gravity would require an unprecedented scale of engineering and investment. Beyond size, structural stability is another major challenge. A massive rotating spacecraft would need to be incredibly robust to withstand the stresses of constant rotation. Any imbalance or structural failure could have catastrophic consequences. The materials used would have to be lightweight, yet extremely strong, capable of enduring years of exposure to the harsh environment of space, including radiation and micrometeoroids. Integrating internal systems in a rotating environment is also complex. How do you connect power systems, communications, and life support between rotating and non-rotating sections, if any? Sealing and maintaining rotating interfaces, such as slip rings or magnetic couplings, poses significant engineering challenges to ensure long-term safety and functionality. Moreover, constant rotation affects everything, from propulsion system design to the operation of sensitive scientific equipment. The energy required to initiate and sustain the rotation of such a massive structure would be substantial, requiring robust and highly efficient power sources. And what happens when the spacecraft needs to change direction or stop spinning? The inertia of such a massive structure would be immense, making flight maneuvers slower and requiring powerful and efficient thrusters. Finally, there's the challenge of human adaptation. Even if the Coriolis effect can be minimized with a large rotation radius, it would still be present to some extent. Early experiments with simulated rotational environments on Earth, such as NASA's Human Centrifuge Laboratory in the 1960s and 70s, showed that individuals can adapt to certain spin rates. But tolerance varies, and initial discomfort is common. Astronauts would need an acclimation period, and not everyone would be able to fully adapt. In short, creating artificial gravity through rotation requires a quantum leap in our space engineering capabilities. It's not just about making a ship spin. It's about building and operating a gigantic space machine, perfectly balanced and integrated, that is safe and comfortable for human beings over long periods of time. These challenges, though formidable, are not insurmountable, but they demand significant advances in multiple areas of technology and aerospace engineering. The financial and technological barrier. Why haven't we built it yet? There are many reasons why we still don't have spacecraft with artificial gravity, and they are deeply intertwined. They combine the technical challenges we've discussed with economic constraints and with the prioritization of other technologies in today's space exploration landscape. Cost, without a doubt, is one of the biggest barriers. Developing and building a spacecraft with artificial gravity would require investments in the trillions. Each space launch is incredibly expensive, and transporting enough material to assemble a structure hundreds of meters wide in orbit is far beyond the current budgets of any space agency or nation. To put things in perspective, the total cost of the International Space Station, the ISS, over its operational life has exceeded $150 billion. And even then, it doesn't have artificial gravity. A ship with simulated gravity would need to be many times larger and far more complex. In the current political and economic climate, with so many competing demands for funding, justifying a project of that scale is extremely difficult, especially since the immediate benefits of artificial gravity for short and medium duration missions still don't outweigh the associated risks and costs. Current launch technology is also a limiting factor. While rockets like SpaceX's Falcon Heavy and NASA's Space Launch System represent significant advancements, they're still not capable of transporting the mass and volume needed to rapidly construct an artificial gravity structure in orbit. It would require a technological leap in payload capacity and launch frequency, perhaps through fully reusable systems with drastically reduced costs, or even the development of space-based propellants and orbital manufacturing techniques, which are still in early research stages. In addition, our current orbital infrastructure is still in its infancy. We simply don't yet have the large-scale assembly and manufacturing capabilities in space that would be necessary to build a giant rotating spacecraft. The construction of the ISS was a complex and time-consuming process, and a structure with artificial gravity would require advanced robotic tools, welding and joining techniques in vacuum conditions, and human or robotic crews capable of performing extremely complex tasks outside the ship for extended periods. Developing these capabilities is still underway and will likely take decades to reach full maturity. Resource prioritization also plays a crucial role. Space agencies and private companies are currently focused on more immediate and tangible goals, such as returning to the Moon with the Artemis program, exploring Mars, developing space tourism, and establishing industries in low Earth orbit. Although artificial gravity is recognized as important for the long-term future, it is not the top priority in the short or even medium term. Limited resources are currently being directed toward the development of more efficient propulsion systems, closed-loop life support technologies, and radiation shielding systems, which are considered more urgent for planned missions. It's worth noting that research into artificial gravity is ongoing. Small centrifuge prototypes have been used in Earth-based laboratories to study the effects of simulated gravity on living organisms. The International Space Station itself has a small centrifuge for experiments with cell cultures and tiny organisms, but it is far too limited to test the effects on humans. Project proposals, like Bigelow Aerospace's Nautilus space station, although the company has faced setbacks, included inflatable modules that could potentially rotate to generate artificial gravity. However, these projects remain in the conceptual or early development stage, and large-scale implementation is still a long way off. The complexity of human interaction with rotational artificial gravity adds another layer of uncertainty. As mentioned earlier, the Coriolis effect can be problematic, though studies suggest that with a sufficiently large radius and an ideal rotation rate, most people would adapt. The lack of full-scale testing with human crews over extended periods prevents a complete understanding of the long-term physiological and psychological challenges. Extensive experimentation on orbital test platforms would be needed before a full-scale artificial gravity spacecraft could be considered safe for crewed missions. In summary, artificial gravity is not yet a reality due to a combination of technical barriers, size, stability, system integration, energy consumption, economic constraints, prohibitive costs, logistical challenges, launch and assembly capabilities, and resource prioritization. While the science behind rotational artificial gravity is solid, the engineering required to implement it at scale in space is still far beyond our current capabilities and our current budgets. The road ahead. When will artificial gravity become reality? While the barriers to artificial gravity are significant, they are not insurmountable. Continued progress in space technology, driven by both government agencies and private companies, is paving the way toward a future where artificial gravity could indeed become reality, radically transforming long-duration space missions and the human exploration of the cosmos. The most promising development to overcome cost and launch barriers is the rise of reusable launch systems. Companies like SpaceX, with its Falcon 9 and soon the Starship, are revolutionizing the cost of space access. As these systems become more efficient and reliable, the cost per kilogram to reach orbit will decrease dramatically. This will open the door for the construction of larger and more complex structures in space, as the logistics of launching components become far more financially feasible. The vision for Starship, with its ability to transport hundreds of tons to low Earth orbit in a single launch, is truly a game-changer in that regard. At the same time, in-orbit manufacturing and assembly capabilities are evolving. Advanced robotics, artificial intelligence, and three-dimensional printing in space are being actively researched and developed. In the future, we may be able to launch only raw materials and autonomous robots to assemble massive structures directly in orbit, rather than building and launching every component from Earth. This would reduce the volume and mass required for each launch and make the construction of artificial gravity spacecraft far more practical than current Earth-based assembly methods. Moreover, the ability to repair and maintain these complex structures in space will be absolutely essential. More efficient propulsion is also vital. For a spacecraft with artificial gravity to travel to distant destinations, like Mars, within a reasonable time frame, it will need propulsion systems that don't rely solely on chemical rockets. Electric engines, such as ion thrusters, or even nuclear propulsion, although still in the early stages for deep space missions, promise significantly higher speeds and shorter travel times. This would make long-duration missions shorter, but they would still require artificial gravity to mitigate the effects of microgravity on astronauts' bodies during the journey. Research in space medicine will also remain crucial. While artificial gravity is the ideal solution, fully understanding the mechanisms by which microgravity affects the human body and developing effective countermeasures is fundamental. This includes improving exercise protocols, specialized diets, and perhaps even medications that can reduce bone and muscle loss. Every breakthrough in this field could help refine the design requirements for artificial gravity, potentially allowing for smaller rotation radii or simulated gravity at levels slightly below 1 g, if the negative effects can be sufficiently mitigated. Another approach that may gain traction is the development of artificial gravity modules within space stations. Instead of building a fully gravity-enabled spacecraft from scratch, we could begin with modular space stations that include dedicated rotating sections where astronauts can spend part of their time. This would allow artificial gravity concepts to be tested in a more controlled and scalable environment, enabling astronauts to acclimate and researchers to study long-term effects in a regime of intermittent or partial gravity. These modules could be attached to larger space stations or even to future lunar or Martian bases to provide relief from low-gravity environments. In the long term, artificial gravity will be essential to humanity's expansion into the solar system and beyond. To establish self-sustaining colonies on Mars or the Moon, or carry out exploratory missions that last for years, the ability to live in Earth-like conditions will be crucial for the physical and mental well-being of space settlers. Artificial gravity, present in large space stations or planetary habitats with rotating sections, is the most viable solution to ensure that future generations of explorers can not only survive, but thrive in extraterrestrial environments. In summary, artificial gravity is not yet a reality, due to a combination of technological, financial, and strategic challenges. But rapid advances in reusable launch systems, in-orbit manufacturing, and space robotics, combined with the growing need to protect astronaut health, suggest that we are on the edge of a new era, an era in which artificial gravity will no longer be science fiction, but an integral part of our journey to the stars. It may take decades, maybe even a century, but the vision of rotating spacecraft carrying humans through the cosmos, protected by the comforts of simulated gravity, is closer than ever. And you? Are you ready to live in a world where gravity is no longer a limitation, but a human achievement? If you enjoyed the video, don't forget to like, subscribe, and turn on notifications so you don't miss any journey through the cosmos. I'm Commander Marcos, and you're watching Stellar Chronicles, where every shadow of space hides a story. Thanks for staying with me, and until the next stellar curiosity,